Good morning. My name is Sid Surya Narayanan. Welcome to the CREW seminar, the third for this semester. This is co-sponsored by the School of Global Environmental Sustainability, SOGIS at CSU. If you're joining us online, please add CREW_collaboratory as a Skype contact and feel free to submit your questions at any time using that ID. I'll be monitoring and moderating that, and I'll be presenting those questions at the end to our speaker. Our speaker today is Professor Wei Qiao of the University of Nebraska-Lincoln. He has undergraduate and graduate degrees from Zhejiang University in China, and another master's from Singapore MIT Alliance, and a PhD from Georgia Institute, all in EE, except for the one in computation for engineered systems from Singapore, right?
Yes.
Okay. He holds a named assistant professorship at UNL in the Department of Electrical Engineering, and he's the recipient of several awards, and I believe the most significant of that would be the National Science Foundation's Career Award he received in 2010. So without further ado, I'll ask Professor Qiao to give us his talk.
Right. Thank you very much. Well, good morning, everyone. It's my great pleasure to give a presentation here. Thank you for inviting me. So, okay, should I? So today I'm going to talk about condition monitoring, online condition monitoring for wind turbines, which we use electrical signals is unusual from traditional condition monitoring method for wind turbines. So we call this method, this technology, non-intrusive technology, because we only use existing signals from the control system of wind turbines. We don't use any additional sensors or data acquisition devices. Okay, so outline of my talk. First, I give a brief background introduction of this research. Then I briefly talk about the current-based, which is current means the current measured from acquired from the terminals of wind generator, electrical generator. Current-based online condition monitoring for wind turbines, which is a non-intrusive method. And I will introduce this theoretical foundation of current-based condition monitoring, why we can use current for condition monitoring for wind turbines. Then the key issue in condition monitoring is fault signal extraction, to extract the signatures of signal which are related to fault. Then actually we developed a method which is called 1P. 1P is actually rotating speed of wind turbine, which is called 1P speed or 1P frequency. 1P invariant spectral analysis. Now I will apply this method, show some application of this method to detect different type of fault in small wind turbine systems. Wind turbine imbalance fault and the fault in the wind turbine bearings. Then I will summarize my talk by some concluding remarks. Okay, so I think everybody knows that wind turbine, they are the big machines, big wind turbine are big machines installed on high towers in remote areas, right? Usually distributed in remote areas, very distributed generating units, and distributed over large geographic regions and subject to harsh environment like offshore wind, even the onshore wind turbines, and the high failure rates compared to traditional generators, generating units, like a power plant, coal power plant, nuclear power plant. Wind turbines actually are subject to a high failure rate. Okay, so that's why the maintenance cost of inspection and maintenance cost for wind turbine systems are very high compared to traditional generating units. For offshore wind, the maintenance cost of wind turbine probably constitute from 15% to 25% of the total cost of electricity generated by wind. And for onshore wind turbine, this ratio is a little bit low, but it's still high compared to traditional generating units. So condition monitoring is an effective means to improve wind turbine reliability, capacity factor, and lifetime, reduce wind turbine downtime and operation and maintenance costs. So most existing technologies for wind turbine condition monitoring diagnosis require additional sensors. Actually, they use additional sensors and the data acquisition devices to implement. The most commonly used sensors like vibration sensors, okay, and other sensors are also used in the condition monitoring, like acoustic emission sensors or other special sensors. So those sensors are usually mounted on the surface or buried in the body of wind turbine component, you know, and they are difficult to access during wind turbine operation. The use of additional sensors and equipment, of course, increases the cost and the complexity of your system. You know, you have the wires, you know, and for those sensors and the data acquisition devices. And another issue is the sensors. Actually, you add sensors to do condition monitoring, but the sensors and the devices are also subject to failure. Actually, sensor failure constitutes a significant portion of total failure in wind turbine systems. According to some statistic data, the number is around 15%. So 15% of failures in wind turbine actually are sensor failures, and another 30 or 40% of failures, you know, caused by failures in sensors. Okay, so you add those devices to solve the problem, but in the meantime you create some new problems. So it's a desired developer, you know, some non-intrusive, low-cost, reliable technology which fully utilize the benefit of condition monitoring for wind turbines. And then we come up with this idea. So the objective of this research is to develop online, so which means we can do this in online instead of you know, stop the turbine and do some offline test. So we do it online, and non-intrusive means we don't use any additional sensors. Okay, we just use existing, you know, sensors. We primarily the sensor used in the control of generators, wind generators, for condition monitoring of wind turbines. So in this research, actually, we heavily investigate the use of current sensors, but it's possible to use other like a voltage. I think, but the current may be better than voltage. You know, it contains more information related to system operation, and then we don't need any additional sensors. So then this figure illustrates the basic idea. So we have this wind turbine. Then depending on the different wind turbine manufacturers, in some wind turbines, the current voltage sensor are actually installed in this part, you know, close to generator and on the tower. And in some wind turbine system, the current and voltage reducers and the power electronics converters actually are installed on the ground, in a cabinet in the ground. This depends on the manufacturers. So we can acquire this voltage and current measurement, you know, which are already used in the control system of wind turbine, and they use this measurement to do condition monitoring. Basically, we develop some method to extract the signature filters related to defects or faults or failures in the mechanical system or electromechanical system of wind turbine. Then based on the filters we extracted, then we can evaluate, for instance, develop some method like a pattern classification method or stochastic analysis method to evaluate the physical condition, real physical condition of wind turbine, and we can determine when maintenance is required. So this slide shows the primary components to be monitored in wind turbine system, and the typical failures in those components, like the blades, have like imbalance aerodynamic asymmetry, surface roughness, and vertical cracks on the surface, and other type of faults. And a troublesome component in like some wind turbine, like the wind turbine with defect machine, double-fed induction generator, the gearbox, you know. The failure rate of gearbox is not the highest, but it takes the longest time to repair or replace a gearbox. So the downtime caused by a failure in gearbox is the longest among all the failures in the wind turbine. So then the defect of failures in the rotor shaft and the generator and your mechanical system. So this presentation will focus on condition monitoring of bearings and rotor and blades for small direct drive wind turbines. We do have some project, another project to investigate the failures in gearbox, but I'm not going to present that. So this talk is focusing on the small direct drive wind turbine, the wind turbine equipped with small permanent magnet machines without gearbox. And but the method I present here is applicable to large wind turbine systems with or without gearbox. So all the defects or failures or faults in the wind turbine system can be classified into two categories, bigger category. The defect or faults without characteristic frequency, and the faults with characteristic frequency. Okay, so then you will need to develop a different method to detect this different type of fault. The faults without characteristic frequency are usually the defects in the turbine in the turbine component in early stage, like we call it the incipient fault. At the early stage of a fault, probably is no clear characteristic frequencies. The features related to the failure probably is widespread over the frequency domain. We did observe this phenomenon actually. So for this type of fault, we needed some different method. Instead of frequency domain method, we probably need the time domain method or time frequency domain method. We have got some result on this, but I'm not going to present this here. So today I'm going to focus on this second type of fault, the fault with a defect or failures with characteristic frequency. Actually, this type of fault can also be classified into two subcategories. One category is, okay, the fault is, characteristic of fault is closely related to 1P frequency, which is the rotating frequency of the machine, okay? Some fault has demonstrated characteristic frequency at 1P frequency, okay, or multipliers of 1P frequency. And some other, there are other faults which demonstrate characteristic frequency are not closely related to 1P frequency, which means they create a new characteristic frequency, like some faults in bearings. I will show that. So, but for this two subcategory of faults, we can use the same method, the frequency domain method, okay, to detect to extract the features of faults. So next, I'm going to talk about the theoretical foundation of current-based condition monitoring. Actually, the principle of this current-based condition monitoring method is quite complicated. It's related to modulation of current signal with mechanical signals like torque and everything. So the details, I'm not going to present the mathematical details. So I'm going to just give a very simple example to show why we can use current for fault detection. But the details is in a paper still under review. So, well, we just look at a very simple case, okay? For healthy wind turbine, we assume that current is sinusoidal. Of course, in the real system, the current has sinusoidals, okay? But we only look at the fundamental component. So this is IH means healthy wind turbine. So this is suppose this is a sinusoidal, okay? The current is a sinusoidal. So it's A times is a sine wave, and omega 1 is a fundamental frequency of current. Then a failure in wind turbine, usually in mechanical system, okay, usually cause a vibration in torque, and therefore the vibration in shaft rotating speed actually. At a certain frequency, we call this a fault characteristic frequency, okay, and which can be detected by, of course, by vibration sensors. I I want to say the vibration sensors are very useful. They can detect majority of failures in mechanical system. Okay. Then the shaft rotating speed for wind turbine with failures, we can represent. This is also simplified representation. This would be, for instance, at a certain time, maybe during a short period of time, the turbine is operated at a constant speed. So this is like B is like a constant speed part with this vibration. This is caused by failures. Okay, we assume this is also sinusoidal. The oscillation is sinusoidal. This is, approximately true. But of course, the real system signal is more complicated. They have other components. But this is just for as an illustration. Then the modulation. Then current is modulated with speed vibration. Okay, so which means the current of a field of a 40 wind turbine, can be represented by this way. Okay, then this component for healthy wind turbine modulated with the speed. Okay, then this vibration term in the speed will appear in the current. So we just apply some, expand this function. We can get this one. So we have the three terms basically: omega 1 and omega 1 minus omega 2 and omega 1 plus omega 2. This is three component frequency. Okay, but the real system is more complicated. Okay, so for most mechanical failures in wind turbine, the characteristic frequency is lower much lower compared to the electric signal, fundamental frequency of current, because particularly in small, the direct drive wind turbine system, the generator has a high number of pole pairs, so the fundamental frequency of current is much higher than the mechanical rotating speed. Okay, so if usually we have like omega 1 larger than omega 2. Then this two component, value will be very close to omega 1. Then if you directly use the spectral analysis, you won't be able to separate these two components from omega 1. So they will, be together. So then in practice, the current may also have harmonics in the integral multipliers of multiples of omega 1 and low frequency oscillations. If you connect the wind turbine to a grid, then the grid may induce some low frequency oscillations to the wind turbine. This is related to grid characteristics. This is a characteristic frequency in the grid. Low frequency oscillation. So the low frequency oscillation is a very common phenomenon in power grid, right? Even during normal operation. But this component is okay because they are not modulated with current. They can be easily separated by using the Fourier transform, FFT, because it's just added to the current. They are not modulated like this way. Okay. Okay. So there are two types of, as I just mentioned, two types of fault characteristic frequency. One is one type of force of defects. The characteristic frequency are related to 1p, or exactly at 1p. Or MP, okay? N is an integer. And some fault may create a new characteristic frequency, so which means not same as 1p, it's different, okay? So in order to effectively detect the characteristic frequency in current signal, then we need a demodulation. There are many methods to demodulation, but there are two very simple methods, okay? The first method is just to use the current square, a square current. Okay, so IF square. Then by using this square, we can see the omega 1 of this signal. We can see that we have more component: omega 1, omega 2, 2 omega 1, 2 omega 2. Sorry, this should be omega 1, not 2. Sorry about that. And 2 omega 2, and the other two components same as the original signal. Okay. Now, if the omega 2 is much lower than omega 1, we can detect omega 1, separate omega 1 from omega 2 effectively. For the characteristic frequency, omega 2 can be separate. Then another method I think is more useful based on our investigation is to estimate the fundamental frequency of the current. which is proportional to shaft rotating speed, which means the rotating frequency of the fundamental current. That's, you know, so if we can detect that part, then the rotating frequency of the current actually is, which is proportional to the rotating speed, 1p frequency, because of the number of pole pairs. It's just of the generator. It's just this term. Okay, so if we can extract this term directly by using some method, one commonly used method is like a phase lock loop method. Okay, there are some other methods based on the current, particularly for permanent magnet machines. By using the current and the terminal voltage, we can very accurately extract the rotating speed of the machine. Okay, this is actually an area of research. Those methods can be used for sensor-based control for electrical machines, motor drives. Yeah. So then we can extract by using this frequency demodulation. We can extract directly the vibrating term, which are related to which is a fault characteristic frequency. Okay, there are other challenges in condition monitoring in wind turbines. Because the fault characteristic frequency, even they are related to, it depends on the shaft rotating speed, right? But the wind turbines are usually operate at the variable speed condition. So the speed is variable, they are not constant speed, okay? So the fault characteristic frequencies are not constant, okay? So because of this, we cannot directly apply frequency domain method like a spectral analysis, okay? So we need to special the handling this this is called non-stationary operation. Okay, so traditional method of FFT spectral analysis works very well for like stationary signals. Okay, so we need some technology to handle this. So I'm going to present the method we developed in this project, which is called 1P environment. So even the rotating speed of the wind turbine is variable, but we did some signal processing to make this rotating speed constant. This is a kind of a normalization in the frequency domain. Okay. Then we use this method to detect the different type of fault in wind turbine system. Okay. So as I mentioned, we can use current signal directly, right? We can use current square, which is demodulated. Actually, current square is related to amplitude demodulation. Okay. So this is a schematic diagram of the method using current or current square. Okay. So basically, we sense the current, stator current from generator terminal. We only need one phase current. Okay. Then we do sampling, okay? The sampling rate depends on your system, your control system. Okay, then we get these current samples. Okay, then if the sampling frequency is low, okay, which cannot satisfy your requirement, you can do this upper sampling interpolation, okay, to increase the sampling rate of this signal, okay? Okay, but it's not necessary actually. Depends on what sampling frequency you have in this step. Okay, so if the sampling frequency is high enough, then you don't need this step up sampling. Okay, then we have this up sampled signal here. Okay, then from this up sampled signal we can estimate the frequency, fundamental frequency of current. Okay, because this information, this fundamental frequency actually is variable because of the variable rotating speed of the wind turbine. This is a variable, okay? So then, but this signal provides some information, so we choose some base frequency, okay? Some base frequency, okay? For instance, we can choose, this base frequency can be a constant, which is a frequency we want to normalize. You know, we want to convert our 1P frequency to this value. For instance, this can be selected as a nominal speed, rotating frequency of the system. Okay, so we choose this base frequency. And then we do this variable rate downsampling. So downsampling, which means we resample the signal, okay? Then we choose this upsampling, the downsampling step size. This is a variable step size, depending on which depends actually approximately proportional to rotating speed. Which means if the during a certain period, if you have a high rotating speed, then you probably need smaller number of samples. Okay, if you have a low sampling rate, you probably need more samples. Okay, so by doing this, we can convert this variable 1p frequency to a constant 1p frequency. Okay, this is the basic idea. Okay, so we have this downsampled signal here. Now, in this signal, the 1p frequency is constant. Okay, then because the 1p frequency is constant, then the fault-related frequencies, characteristic frequencies also become constant. Then you can apply the class standard spectral analysis method, FFT, whatever. Then you will clearly see this fault characteristic frequency in the spectrum of current of this processed current signal. Okay, so this then the second diagram, which actually very similar to this one, but in the second diagram, we use the estimate the current frequency instead of current or current square. Okay, so most of the steps are same. Just here we estimate the frequency of the current by using the PLL. Then we can get the which is divided by the number of pole pairs, we can get the shaft rotating frequency. Okay, this is directly the rotating speed. Okay, we estimate. Okay, then we can apply the same method to the shaft rotating frequency instead of current signal. Okay, so this is another signal. Okay, we estimate. Then we can get the same result, but this is directly this method we directly look at the frequency, rotating frequency. Okay. Okay, then we did a lot of tests on small wind turbine systems. This is a testing facility we actually designed and constructed in our lab. A wind tunnel. The dimension of the tunnel is 8.2. The cross-section area is 8.2 feet by 8.2 feet, and the length of the wind tunnel I think is 23 feet. Yeah, and the wind flow in the tunnel is controllable, which is generated by this big fan, 7 feet diameter fan. The fan is driven by a 60 horsepower motor drive, adjustable speed motor drive system. So we can adjust the speed of the fan and to generate the wind flow at a different speed. Okay, so this is a wind turbine we we tested, which is a small wind turbine made by Southwest Wind Power, air-breeze wind turbine. This is a very popular small wind turbine, right, in the market. Yeah, this just shows the facility, and this is a data acquisition system, and the fault detection algorithm was implemented in this lab computer. It's a very simple system. The power generated by wind turbine is consumed by the load, or we can also connect to the power grid. And this is a data acquisition for current signals. So we only use one phase current here. Okay, so the first fault we tested is a blade imbalance, which means in this test we added some additional mass to one blade of the 3 blades, and this makes the system unbalanced. So the experiment we did a lot of experiments, but here I only show some typical results. The experiment was performed in 5 scenarios. Okay, first is a baseline case, which means the turbine is healthy, no unbalance. Then we did other 4 scenarios. The mass density of one blade was increased by 1.25%, 2.5%, 3.75%, and 5%. This is not a large, right? It's still very small. Even the 5% increase in the quality of that blade, and other 2 blades were unchanged. Okay. Well, so this is a result when we use current directly. Okay. You can see in this system, this imbalance fault, the characteristic frequency of imbalance fault is a 1p frequency. Actually, it's 1p frequency. So if the 1p frequency is modulated with current, then we actually in the current the characteristic frequency of the fault becomes 50 and 70 hertz. That's omega 1 plus and minus omega 2. So that becomes, because we normalize the current, we use a 1P environment, normalize the current frequency to make the current frequency, convert the current frequency, fundamental frequency of current to a constant value of 60 hertz. This is a great frequency. So then the 1P frequency corresponding to the 1P frequency is converted to 10 hertz for this system. Okay? So which means the system has the generator has the 6 pole pairs. Okay? So then the characteristic frequency will be 50 hertz and 70 hertz. This is very close to 60 hertz. So it's very difficult to say this characteristic frequency, in current signals. Okay? Then if we zoomed in this figure, and this is a result around 50 hertz. So we just zoom in this part and this part, and this is a result around 70 hertz. Okay, well, we can see only in the worst scenario, 5% increase of the quality of the blade, we can see this excitation, but for other 4 scenarios, it's difficult to see, right? The characteristic frequency component. Okay? So this is a limitation of using the current directly because the omega 1 is much, much larger than this omega 2 as I mentioned before. Okay, then if we use estimated shaft speed, result is much better. Okay, here. Okay, so we don't need to worry about a 60 hertz component. Now we look directly at 10 hertz. This is 1P frequency. So we can see the excitation is clear at 10 hertz, right? In the PXD of the estimated shaft frequency, which is estimated from the current. Okay, so we zoom in this part, then we get this result. We can see it's very clear. The different scenarios, 1.25%. This is a baseline case, okay, and 1.25%. This is 2.5%, and this is 3.7% and 5%. So all the cases, the characteristic frequency, the excitation for all the scenarios can be clearly detected. Okay. So this is the benefit of using the ST modulation. But look at the rotating speed instead of the current directly. Okay, here this just shows the result by using the standard PSD, so without any upsampling, downsampling that process. Well, you can see because the 1P frequency, the wind turbine was operated at variable speed in a large speed range. So 1P frequency is variable in the range of 6 to 13 hertz. This is variable because the rotating speed is variable, was variable in the test. Okay, so it's very difficult. See, from the spectrum, it's very difficult to quantify where the characteristic frequency is, right? Okay, so this result shows that why we need to use this 1P invariant to convert the 1P frequency to constant value. Okay, here's another test on imbalance fault, the bent blade. In this test, we didn't add any additional mass. We just, this blade was bended, okay? So this also created some kind of imbalance. This is a kind of aerodynamic imbalance, okay, asymmetry in the system. So there's 2 different band blades. We can do this edge-wise and also this flap-wise band. So in this test, we just did, I think, this tab. Okay, so one blade was bended, okay, and the other 2 blades was unchanged. So we bended the blade at a different level, okay, degrees, 2 degree and 4 degree and 6 degree, okay. So this is a different severity of this fault. Okay, so we can see this is an estimated result of using the 1P invariant method and use the estimated shaft rotating speed. You can see clearly the excitation is excitation are very clear at is 10 hertz. Okay, again. Then we zoom in the result here. Okay. So this the healthy case, and this is a 2 degree, 4 degree, and a 6 degree. It's very clear. All right, other imbalance faults we tested. Let me see this one. Okay, in this one, this test we broke the magnets of the generator. So which means the generator has many magnets embedded in the rotor. Actually, on the surface of the rotor, this is a surface mount permanent magnet machine. On the surface of the motor, I think there are maybe 40 or 50 kind of magnets. So we damaged one magnet. This created some kind of imbalance in the electromagnetic field in the generator. Okay, so we compare the failure case with a baseline case. So yeah, obviously this is very easy to. This method is very easy for this method to detect this fault because this is closely related to electric signal, electromagnetic signal. Okay, it has more correlation between the electric signal and the mechanical signal. Okay, and this is another test. In this test there is the connection between the blade and the rotor of the turbine was loosened. One blade, okay, was loosened. Okay, so this is the blade when the system is rotating. There's some vibration in the blade. Because the connection was loosened. Okay, so again, the red curve is the results of the 40 case, and the green one is the baseline case. Okay, we can also clearly detect this type of fault. Okay, then the next category of fault, type of fault are the defects or failures in bearings, okay, wind turbine bearings. There are several bearings even in this small wind turbine system, okay. And we investigate different bearing faults. One typical fault is we artificially generated this fault actually. This is an auto-race defect, okay, or auto-race defect. So according to theoretical analysis, the bearing auto-race defect has a theoretical frequency at this value, Fc. This is a characteristic frequency of auto-race defect, which is closely related to, this is a fundamental frequency of current, and this is rotating speed. And those are the parameters, dimensional parameters of the bearing here, okay? So it depends on the fundamental frequency of current, depends on rotating speed, but also depends on the dimensional parameters of the bearing. So this is a frequency modulation, okay? And we can see in this type of fault, there's a new frequency component which was created because of this term. It's not just the same as the 1P frequency. Is related to 1P frequency, but it's different, okay? Okay, so this is a defect, auto-race defect, that we created a fault in one bearing of this air-breeze wind turbine, southwest wind power air-breeze wind turbine, and this is the defect we create. Of course, this is a kind of artificially created fault. Later on, I will show some real fault which is generated naturally. Okay. Okay. So by using this our method, okay, we can see this excitations were observed at this frequency, which is very close to 30 hertz. So this is a new frequency. It's different from 1P frequency. 1P frequency is 10 hertz. Okay. Then the theoretical fault characteristic frequency is about 29.9 and 19.1 and 100 hertz. This is can be obtained from this equation here. Okay, that's a theoretical value. But the characteristic frequency are no longer 1p frequency, okay, or multipliers of 1p. But this one is good because it's still close to 3p. Okay. Okay. Then we can see for the house, we zoom in the result here. The red curve is a faulted wind turbine, and the black curve is the healthy wind turbine. We can see there's a significant difference at this frequency. Okay. But no excitation observed for the healthy turbine, but significant excitations were observed for the faulted system. Then this is the result by using the standard PSD without any processing. Okay, no characteristic frequency. Okay, by using standard PSD. Okay, here is another common fault in bearing. In a bearing, it's the broken cage break fault. Okay, the bearing cage breaks. A theoretical characteristic frequency can be calculated. The theoretical characteristic frequency, the shaft rotating speed related to this fault, is this one. This is a shaft rotating speed. So this depends on the rotating speed of the wind turbine, FR. This is the rotating speed of wind turbine, 1p or 1p frequency, 1p speed. And those are the parameters. Again, dimensional parameters of the bearing. And then if we look at the current signal, the current signal, theoretical characteristic frequency in current signal will be modulated with the speed. So we have this fundamental current, which is modulated with speed, similar to the previous faults. Okay. So again, there may be a new fault characteristic frequency, okay, instead of 1p frequency. Okay, so in this test, instead of artificially create a fault, actually we run this wind turbine with a healthy bearing for 25 hours. But we did some pre-processing. We removed the lubricant of the bearing, but the bearing was healthy before testing. Okay, so the system was operated for like 25 hours until it failed. The turbine stopped running. Okay, after 25 hours in this wind tunnel. Okay, so this is a healthy bearing, and this is a bearing with a broken cage. Actually, there's two failure points. There's two failure points. Okay, this is not artificially generated. This is a self-created fault. Okay. All right, so then we apply different methods. First, we look at the method of using current signal directly. Again, the characteristic frequency of this type of force in current is 60 Hz. This is a fundamental frequency of current, modulated by the characteristic frequency of the force in speed. This is 4 times n. N is integral 1, 2, 3, and so on. Okay, so one characteristic frequency is 4 Hz, and 8 Hz, and 12 Hz, and so on, the multiple characteristic frequencies. Okay, so for the healthy bearing, it's difficult to see, right, from this spectrum. This is a current spectrum. Even we use the 1P method, 1P invariant method. Okay, so if we zoom in the result, we still can see a little bit difference here. This is around, so the two characteristic frequency will be around the 60 Hz. One is 56, the other is 64. So this is around the 56, this is around the 64. We can see some difference, but it's difficult to tell. Which one, maybe it's caused by noise or whatever other factors, okay, instead of force. So it's not good to use current. Then we use this estimate current frequency, which is proportional to rotating speed. So which means we use rotating speed directly. So we extract that 4 times n component. Okay, so we can see this is a healthy wind turbine. Okay, and there's no excitation at 4 Hz or 8 hertz. Those are 1p, 2p, and 3p, just the characteristic frequency of the healthy system. Okay, there's no excitation at no excitation at this part, 4 hertz and 8 hertz. This part, this is 10 hertz. So no excitation at 4 and 8 hertz for healthy system. Oh, okay. This is one invariant PSD of the estimate current frequency at the 10th hour in the test. So 10th hour in the middle of test. Okay. We can see 4 hertz and 8 hertz clearly. This is a 4 hertz component, 8 hertz component. Okay, clearly observed. Okay, in the spectrum. Okay, actually at 10th hour the system was still operating. The bearing was in sub-healthy condition. It already has some defect. Okay, maybe the cage is not totally broken yet. Was not totally broken yet, but there's some defect on the cage. But the system can still operate. Okay, this is close to the end of test, the 20th hour. Okay, the 20th hour. We can see the 4 hertz excitation become a little bit larger compared to this one, and this 8 hertz excitation. Okay, so by using the estimated current frequency, you can clearly detect this characteristic frequency of this type of force. All right. So the conclusion: failures of wind turbine induces component, okay, with 1p dependent characteristic frequency. It doesn't matter. Some fault characteristic frequency is just the 1p frequency. Some fault characteristic frequency are not different from 1p frequency, but it depends on 1p frequency and the parameters of the component, dimensional parameters of the component. Okay, and this 1p independent frequency component in the speed in the torque, which is modulated with current signal. Okay, so current signal may also contain the harmonics and low frequency oscillating component, but this we don't worry about this those components because they are not demodulated with fundamental frequency. They just add to the fundamental frequency, and it can be easily separate from the fundamental frequency by using the frequency analysis method. Spectrum analysis method. So in order to detect different failures, defects in wind turbine system, demodulation is usually required. There's 2 simple demodulation methods are presented. One is using current square, the other is using the rotating frequency of the current fundamental frequency. Okay. Then we develop a spectral analysis method. We call it the 1p invariant spectral analysis method to effectively detect for condition monitoring of wind turbine and to detect the failures or defects in wind turbine by using only one phase current signal. And I have shown a lot of experimental results to demonstrate the effectiveness of this method for condition monitoring of small direct drive permanent magnet machine wind turbines. Okay, and yeah, we are working on large wind turbines. So I would like to acknowledge the financial support for this work from the U.S. Department of Energy and the Nebraska Center for Energy Sciences Research and the Nebraska Public Power District. Well, this is all about my presentation. Thank you very much. I'd be happy to take any questions and comments.
Questions for our speaker?
Yes.
I always have questions, so yeah,
Just a note. If you could repeat the questions that you hear before you provide answers, it would be helpful for all.
Oh, repeat. Okay, repeat the question. Okay.
So I've been involved with the mechanical side of condition monitoring years ago, and so I'm kind of curious why you chose to resample as opposed to control your sampling frequency at the point of sampling. So in normal condition monitoring, what you do is you use a phase lock loop to control the sample frequency as a multiple of the rotational frequency up front. So,
Okay, so the question is, instead of using the variable sampling frequency, why did we use this resampling, right? Process, yeah, resampling process, downsampling, upsampling, downsampling process. Okay, this is a good question, okay. The answer is, okay, because in the wind turbine, as I mentioned, the signals we use is just extracted directly from, used directly by the wind turbine control system. In wind turbine control system, usually the sampling frequency is constant to facilitate the control. So that's why. Now, of course, the other method is probably we do variable sampling instead of you know, downsampling, upsampling. Yeah, resampling the signal. That's possible. But even you do the variable sampling, you still need some information. You still need to get the information of the rotating speed of the system in order to know what variable sampling frequency you need in real time, right? You cannot, yeah. That variable sampling rate should actually related to rotating speed if you want to get the similar result to this method. Well, the principle I would like to say is the same, you know, using different sampling rate at the beginning or resample the signal in the middle. Yeah. Both, I think both work.
They both work, but the second one has numerical issues when you resample. But yeah, we can talk about that offline.
Sure.
The other question I had was, so I presume you're looking at the current between the PMG and the rectifier, right?
Yes.
Okay, so my experience with current sensors is they have a pretty nasty frequency roll-off above a couple hundred hertz. And so did you see problems with basically are you using straight CTs or Hall sensors, and how did the roll-off affect that?
Yes. The question yeah, we used the signals. Current was measured between the machine terminals and the rectifiers. So there may be a lot of harmonics, right? That's your question.
Well, the sensors themselves.
Yeah.
Sensors themselves have
yeah. Also have the
filters.
yes.
So
Yeah.
Pass a very small frequency band.
Yes. Right. The sensor itself also maybe create some, you know, the high frequency component in the current measurement at 100 hertz, right? Component in the current signal. So did we see any problem with that? What current sensors, transducers we use in our test? Yes, we use the Hall effect current sensor. Yeah, which commonly used in control system. Yeah, so we used some filters because I didn't show here, but we have in the signal processing data acquisition system we have some anti-aliasing filter, and also we do have some filter. Actually, it's a kind of type of low pass filter to filter out those high frequency.
So basically, you're filtering off that.
Yes. The current signal is actually filtered. Yeah, we did some hardware filter to filter out certain component because the high frequency component are all not related to fault. We don't care about that. Yeah. Yes.
I have a question from one of our online viewers.
Sure.
Brendan Giels asks, was the run to failure test done with a variable or constant wind speed?
Oh, okay. I think I should repeat the question, right, to other audience. Okay. Were the failure tests, right? Were the tests were done at variable speed or constant speed, right? Yeah. The answer was variable speed because we already showed in one slide this. If we use the standard PSD method, I showed that the characteristic frequency actually was variable from 60 hertz to 13 hertz. This is a big speed range of the turbine. Yeah, we always test the wind turbine in variable speed. Yeah, variable speed. If we operate the turbine exactly at the constant speed, the classic standard PSD would work. Yeah. Sure.
So, in case of multiple simultaneous faults,
yes.
how would your method help identify those, for example, loss of a magnet and a bad bearing, which is not visual,
Okay.
overreact?
The question was because we did this multiple sampling process, and the magnitude of the signal may be affected, and will that have effect on the result, right, for detection, right? Yeah, you are right. Yes, actually, if you do the downsampling, actually you reduce the energy of the signal. Actually, the magnitude of the signal actually will be reduced. But yeah, it's okay because we did all the scenarios at the same base frequency, so it's fair to compare them. Yeah, so you see the result is still clear. If the failure case, then the fault will be clear. And another issue, we can we use a different upsampling ratio for the system, because if the system is in normal condition without a fault, there's supposed to no characteristic frequency. Then we can probably use like a larger upsampling ratio for the faulted scenarios. Then it will be more clear to see the fault characteristic frequency component. Yeah, that's not an issue. That can be handled, right? Any other questions?
In the test that you showed where you went to failure, where you took the lubricants out,
yes,
the last one that you showed,
yes,
you got 2 failures,
yes,
which you probably did not expect to see 2 failures.
The question is,
and how did that show up in the data?
Okay, yeah, the question was, in the last testing result, the cage, the broken cage test, we saw there's 2 points of broken, 2 broken points in the cage, on the cage. So probably we didn't expect that kind of case. So what did we expect before the testing, right? That's the question. Yeah. We didn't know actually before test. We didn't know which part will fail. We think probably the cage, because the cage is kind of a fragile part. The bore, the rays of the bearing, they are very strong, very strong and solid. So maybe the cage is we didn't expect any special.
Did you see it in
just,
your data? Did you see at the 10-hour point,
yeah.
you could see it break at 1 cage, and at the 20-hour point, you saw 2 cages? I mean,
we,
are you able to see the magnitude of what's happening in your signal?
Yes, yes. This is okay. Did we see the monitor the whole process from 0 hour to 25th hour for the testing? The answer was yeah, is yes. We did. I didn't show the result here, but we observed the whole process because we collected the current signal for this 25 hours. Then we did this process, but we instead of using this frequency domain method, we use a 10 frequency domain method. Actually, we designed another method based on wavelet filter to look at the energy of the signal for this 25 hours. Yeah, the curve is like this. For the first 7 hours, the energy of the processed current increases. Then at a certain 7th hour to maybe 19 or 18 hours, this I forgot the exactly what's valued. The waveform is pretty constant, but it's also oscillated. But the envelope of the waveform is like pretty constant compared to the first 7 hours. So then, after that point, the current, the waveform, yeah, is increased significantly during the last several hours. Yeah, that's true. But that's kind of incipient fault, so I didn't show the result here. Yeah, but what we conclude based on that result was that first 7 hours, that's the fault defect was developed very quickly. Then between the second stage, the magnets are almost constant with small oscillations. The system, the bearing was in subhousing condition. Yeah, but was not totally broken yet. Yeah, but after certain time, this maybe because heating, whatever, some other issues, then the system failed quickly. Then the protection system of the wind turbine just stopped. The turbine cannot run anymore. It automatically stopped. Okay. So unfortunately, we didn't stop the system and took the bearing out to see what's happening. Okay, but yeah, from the waveform we can estimate that. Yeah. Okay. Any other questions?
Other questions? If not, thank you.
All right. Thank you very much. Should I stop this or probably need to stop? Yeah, stop this first. Okay, plug out.